Hello students, in this video we'll discuss how to compute the exponential of a matrix that has complex eigenvalues. If a matrix A has complex eigenvalues, let's write them as lambda equals A plus or minus IB, we know that it will come in complex conjugate pairs. We can factor A as A is P, C, P inverse, where C is the matrix A, negative B, B, A, and P is the matrix real part of V, imaginary part of V, where here V is the eigenvector for lambda equals A minus IB. So let's see how this works in practice with one final catch. We can compute the exponential of C using Euler's formula. We'll use the fact that the exponential of the matrix C is e to the A times the matrix cosine B negative sine B sine B cosine B. We'll need to use this fact when computing the exponential of a matrix A. So let's see an example of this. Let's compute the exponential of the matrix 2, negative 1, 13, 6. To do this, we'll find the eigenvalues of this matrix. So we'll find the eigenvalues. I'll compute the determinant of the matrix with lambda subtracted off on the diagonal. Equals 0. Doing this, we will have a lambda minus 6 times lambda minus 2, and then we'll have a plus 13 equals 0. This will simplify to lambda squared. Then I'll have a negative 6 lambda and negative 2 lambda. That's a negative 8 lambda. And then I'll have a positive 12 and 13. That's plus 25 equals 0. The next step is to complete the square. So what we can do is we can write this as lambda squared minus 8 lambda plus 16 plus 9 equals 0. And this term over here will be a perfect square. So this will be lambda minus 4 quantity squared plus 9 equals 0. So that will say that lambda minus 4 squared is equal to negative 9. Taking the plus or minus square root of both sides, I will have that lambda minus 4 is plus or minus 3i. And therefore, the eigenvalues lambda will be 4 plus or minus 3i. Now, we see that they come in complex pairs, and so what I will need is I'll need to find the eigenvector that corresponds to 4 minus 3i. So let's find that eigenvector. So lambda is 4 minus 3i will give us the following eigenvector equation. It'll give us the eigenvector equation 2 minus 4 minus 3i, negative 1, 13, and 6 minus 4 minus 3i. Applied to V1, V2 is 0, 0. So we will focus in on the first equation. This first equation over here will tell me that negative 2 then plus 3i applied to V1 is equal to 0. So I will have a negative 2, and then I'll have a plus 3i. That will be applied to V1, and that negative 1 will be applied to V2. Must be 0. We see from this that I can choose V1 to be 1, and if V1 is equal to 1, V2 will be negative 2 plus 3i, which I will split into real and imaginary parts. The real part of this will be a 1 and a negative 2 plus I, 0, 3. So the first matrix, the matrix without i's, is the real part, and the second matrix is the imaginary part, as it's the coefficient of I. From this, I can form the matrix P. So we see by our factorization that our matrix A is the matrix P, which will be 1, negative 2, 0, 3, times the matrix C. So we need to find out what our A and B will be. My eigenvalue is 4 plus or minus 3i. So the A will be 4 and the B will be 3. So I will have a 4. Then I will have a negative 3. Then I will have a 3 and a 4. And then I put the inverse matrix of this matrix over here. The inverse matrix is found by flipping the diagonal entries, negating the off-diagonal entries, and dividing by the determinant. The determinant of this matrix is 3 minus 0, so every element in this matrix will need to be divided by 3. Now I can find the exponential of the matrix using the fact that P, C, P inverse to the n is P, C to the n, P inverse, and that the exponential of P, C, P inverse is P exponential of C, P inverse. I combine these two facts to conclude that the exponential of our matrix will be equal to the matrix P, which is 1, 0, negative 2, 3. Then the exponential of this matrix, which will be e to the 4 cosine of 3, negative sine of 3, sine of 3, cosine of 3. So this is going to be e to the 4th power cosine of 3, e to the 4 sine of 3 with a negative sign, e to the 4 sine of 3, and e to the 4 cosine of 3. And the last matrix will be P inverse. So P inverse, we can find that. It'll be 3 over 3, which is 1, 0 over 3, which is 0, 2 over 3, and 1 over 3. So by using this special factorization for matrices with complex eigenvalues, I'm able to compute the exponential of a matrix, using the same idea that we were able to compute the exponential of a diagonal matrix, just with a new type of exponential with a special form. Thank you very much.